All right, so hey guys, this is Ignited Minds Lesson 3 for data science, and today we're going to look at working with models. So as an overview, this is the second half of the data science workflow, and the data science workflow, what that is it's the kind of process you have to follow when pursuing your data science projects, whatever that may be. So in the last lesson, we looked at working with data, which is the first half of the workflow, and that involved data collection, cleaning, and data analysis. This time, we're going to look at working with models, which is actually using that data and putting it into a model, basically, and I'll explain what that is later. So this involves two steps, model building and model deployment. But this graphic actually says the second step is model deployment, but I will be using another step that I made up called post-model work, which involves 3 actual steps that I feel are more accurate: testing, deployment, and maintenance. And deployment is only one of those 3 factors. So as a recap of working with data, data collection is basically taking your raw data and putting it into a usable format for your project. So obviously the first thing you need for a data science project is data. And you can take that in things such as surveys or experiments. But what we're doing is we're taking it and then we're putting it into a usable format online for your project, such as in a CSV file. The second thing is data pre-processing, where you take that usable format and you put it into a modelable format. So before you want to put it into your model, obviously you have all this data, but some of it might not be accurate. And with data pre-processing, you want to take all that dump of data and make it into an accurate format. And the third thing is data analysis, where you take that modelable format and you make findings out of it. And with those findings, you'll then create a clear presentation of your data science project. So that's just a recap of last time. And what I'll do is I'm gonna take a look at an actual real world data science project and show you guys those steps in action. So if you guys don't remember, here we have a Alzheimer's detection model, and it uses the programming language R. I created this a while ago. So I'm not going to read the whole thing, but here I can show you guys a overview of what I've done. So the first thing is the context of the problem. Basically, in a team of 6 other people in the summer, I basically took a data science data set of patients with Alzheimer's, and I wanted to answer this question: how can we determine cognition levels with physical brain anatomy? Or basically, I was asking, how can we determine how well your brain functions just by looking at the parts of your brain? So in this data set, there were 2,700 rows. Each row represented a unique patient. And then they had 57 columns about them, representing things about them, such as like their ID, age, or their symptoms of Alzheimer's. And ultimately, the variable I was looking at was their diagnosis, which came in 3 levels. So 0 was no Alzheimer's, 1 was mild Alzheimer's, and 2 was severe Alzheimer's. So if we look back at the parts of a data science project, we first have data collection. And in here, you can see the data collection with the data set. Let me show you guys the data set. So you can't see the data set on here, but I've used a data set. Let me show you guys that real quick. Whoops. All right, yes. So you can see the Alzheimer's data set right here. And you can see every single one of its patients in the left column. And then here you can see things about them, such as their diagnosis right here, 0, 1, or 2, their age, which was usually around 68, their education, whether they were female or male, and more things about them. And as you can see, I didn't collect that data. So usually in a data science project, what you'll see is different parts of the data science workflow are handled by different people. So even though I didn't create the project, I didn't create the data set, I still created the main project. And so as you can see here, I use the read CSV function to read the data from this data set, which the link was right here. And I put it in a variable called AD. All right. So, and basically what I did was I split it into training data and testing data. And I'll explain what that is later, but that's basically used for my model. The next thing we have is data pre-processing. And what that is basically putting your data in a more accurate position to be used for your model. Here, I only had to do one thing for that, which was omitting the NA values because you can't really work with values that are not applicable. And the next thing is data analysis, where you make your findings and you present those findings in a clear presentation. And to recap, I had three major findings before moving on to the model. The first one, and usually with data analysis, you put them in graphs like this, which is why it's important to learn about graphs in math, as they have many functions in the real world like this. So the first one was I compared the diagnosis and the brain volume. And although you might think that changing your diagnosis of Alzheimer's would severely change your brain volume, it actually didn't. So in data analysis, you might encounter things opposite of what you might expect. So if you encounter this, you must look closer. So while looking closer, we actually saw that the diagnosis went up when the CSF volume went up when the diagnosis went up, but the actual brain tissue volume went down when the diagnosis went down. So just looking closer into the actual parts of the brain gave us this new insight. And basically, this going down and this going up kind of balanced out for this to be the same. And what we found out was that the actual brain tissue volume, which was the part of the brain that actually does thinking, was went down. So yeah, but now that was just a recap. Now let's go on to building the model. So you might ask yourself, what is a model? Well, a model is kind of a computational representation of a real world process. And basically here, we're trying to represent Alzheimer's detection, meaning we're using this model to kind of predict Alzheimer's in people. So after our data analysis, we went into a regression model. And a regression model is one of two types of models, two main types of models. There are many other types of models that we don't really have time to go over, but what a regression model basically is a type of model that aims to determine the strengths of relationships between certain variables. And so basically, like, if you have two variables, like the diagnosis and then the different parts of the brain, each part of the brain will be a variable, and the diagnosis will be the main response variable to those variables. So you want to determine the strength of the relationship between each part of the brain and diagnosis to see which has the strongest relationship, to see which part of the brain causes the most Alzheimer's. And another type of modeling technique is classification, where you just want to classify certain variables as certain things, but we're not using that here. But here we combine two types of regression models. We combine multinomial regression, which is a type of regression that allows you to deal with variables that are more than just binomial or more than just two options. And here we see that in action because we have diagnosis 0, 1, and 2, which has three options rather than just two. And we're using lasso regression, which stands for least absolute shrinkage operator. I forget what the other S stands for, but the main point is just that this is aiming to do regression, which is determining the strengths of variables with variable shrinkage. And what it does is you have all these variables here. You have the left hippocampus, the right hippocampus, the frontal cortex. Those are all just different parts of the brain. And they're comparing it to the diagnosis. And what lateral regression wants to do is see which one has the strongest, plays the strongest role in order of, predicting your diagnosis. So here we have multinomial lasso model, and the model is actually just a piece of code. So it's nothing like a really big scientific model that looks all fancy and everything. Just a piece of code. And so here, and for different types of models, you'll need to know how to code them differently, but you can just look online for each one. In our case, since we're using multinomial regression and lasso, we have to use this function called cv.glmnet. And what we're doing is these are different parameters in your code, or different things you can get input in your function to make it work. So there are 4. Let's break them all down. The first one is x. And x we put in the data ourselves. So we're making a data matrix of all these variables. And these are different parts of the brain. So frontal cortex, the left temporal cortex, the left hippocampus, and the right entorhinal cortex, and more things like that. And we're comparing it to our diagnosis. And this TRD basically is the training data above, where we split it into training data right here. And that's just the part of our data that we're using to train our model. And then what we're going to do is we're going to test our model with the testing data. Yeah, so we're going to test our model with the testing data after, which is new data that it hasn't seen yet, to make sure that it works well. Okay, so yeah, here we have the multinomial lasso model. And then the third parameter is family equals multinomial, which specifies that it's multinomial. And alpha equals 1 just specifies that it's lateral regression. So from that model, we have 3 different, types of 3 results. So here is for diagnosis 0. We see the strength of every variable in determining a 0 diagnosis. So as I said earlier, lasso performs shrinkage. And basically, if there's a dot here, it means that it plays basically no role in determining a 0 diagnosis. But the higher the number, the higher the absolute value of the number, meaning either a higher positive value or a lower negative value, means a stronger relationship. So here the highest thing is the left hippocampus and the right hippocampus. And as we see in the 1 diagnosis, it's actually the right temporal cortex that plays the biggest role. And with the 2 diagnosis, it's actually also the left hippocampus. So in the extreme cases, the 0 and 2, the left and the right hippocampus play a very big role. So with your model, you can basically find things like this when you look out for the small things. Now we're actually using a classification model. But before we do that, I know I'm rambling on a lot about this. Let's just look at models in general. So as I said, a data science model is a computational representation of a real world process. And in this model, that's basically what we did. We have a computational representation of Alzheimer's diagnosis by determining the strengths of different variables in determining the diagnosis, and by looking at the strength of each variable and determining that, we can know what to look out for in real life as well. And the first type we looked at was regression, which was looking at the strength of each variable and determining that. But now we're going to look at classification. And classification basically puts variables into different categories or classifies them based on certain values. Now, here, what we did was we used regression first. We actually used two models. So the first model was regression. We used that to determine which variables to use in determining the diagnosis. Now in classification, we're going to use those variables as they have the strongest relationship with diagnosis and using them to classify each patient as a certain diagnosis. So here we're using a certain classification model called random forest. And as you can see right here, we're in random forest. We're comparing the diagnosis to every single part of the brain where we saw was the most important. The left hippocampus, right hippocampus, and all these three other parts. And we're using the training data. But this time, as we can see right here, we're using the predict function to predict the testing data using the random forest model. And as you can see, every patient now is classified as either 2, 0, or 1, which are the different types of diagnoses. And since it did it correctly using the testing data, which is data it's never seen before, we can say that this model is accurate. And so generally when building your own model, I want to give 3 tips. Number 1 is choosing good variables. Now, I was able to do that well with the regression model, which limited it to just 5 variables. The second is to understand your model conceptually. If you have a good basic understanding of how your model works, you'll be able to know what it's used for and how you should efficiently use it, which leads into my third tip, is to select your most efficient and appropriate model type for your situation. And for me, that was the random forest model and the multinomial and lasso model. You're going to want to research more types of models for different types of projects as well. Now, the final step in the second stage of the data science workflow is the post-model work. And I just like to call it that because once you're finished building your model, you want to do 3 things. So the first thing is model testing. You want to make sure that it's totally accurate. And you want to make sure that the code is accurate and the model is accurate. So you want to test your code with test cases. Now, the reason I have S underlined is because you want different test cases. So let's say you have a function that generates a random number. In that function, and it generates a random number based on, your based on key you click. So you're going to want to click multiple keys to see if it works in every case. And that's what you're going to want to do here. And you're also going to want to test models with new test data, which, as you can see, is what we did here. Not only did we use the random forest model, we used it in a function called predict, using the test data to actually finally predict the patient's diagnoses. The second is to deploy the model. And you're going to want to deploy this to the real world. Now, this is usually handled in big companies by people who aren't even data scientists. So you won't really have to worry about it. Technically, I deployed my model on Kaggle, which is the online data science platform I used here. It's free and it's easy to use for anyone online. You guys can even use it too. But basically what you're going to want to use is to pick the right platform to deploy it to. So the only reason I picked Kaggle is because it's the only thing that I can actually use. But in the real world, you're going to want to use like paid platforms that are very expensive and that are used at a high level. But even I don't know how to do that. And you're going to want to learn how to do that once you get to that high level. But again, it probably won't be handled by a data scientist anyway. And the final part is model maintenance. And when maintaining your model, you want to continuously check for issues. Basically, after you create a model, it won't be finished. You're going to have to, since data science is a very rapidly evolving field, because that's how it got to this stage, it's built on data, and the data of the world changes as time passes. So obviously, as the data passes, your data science model might become less relevant, which is why you're going to have to update to maintain your relevance. And to do this, you can periodically test it with new updated data and see how that works. For example, with my data set, with my data set with Alzheimer's, what I can do is I can replace this testing data split with new data of new Alzheimer's patients and keep running this model with those new Alzheimer's patients to check the accuracy over time. And if the accuracy stays the same or doesn't fall off, then I'll know that the findings are still accurate. But in Alzheimer's, there could be things such as new findings about the brain. As you know, there's obviously no cure yet. And it's just in every single different domain or field where you put data science in, like I put it in Alzheimer's, or you could put it in any other field, such as like any other disease or your business or anything like that. Things change, and you're gonna have to periodically test it with new data. And you're also going to want to check for code issues as well, which, in all of computer science, there's going to be things like that. So just look out for user complaints like that. So originally I was planning on showing you guys how this would look in a project by going through another project. But I feel like, in the first Alzheimer's project, that already covered everything pretty much. So I think if you guys want to look at this project, I can send you a recording and you can skip here and you can enter this link into your computers. But I won't go over that whole project right today. So yeah, that brings us to the end of our lesson, and thank you for listening. Do you guys have any questions?
No.
Okay. Well, yeah. Thanks for being patient. Thanks for listening, and thank you for your time. I'll see you guys all in the next lesson, which might be in either 1 week or 3 weeks. So yeah, thank you all again, and I'll see you in the next lesson.